Dear students, in this session we are going to learn how to determine the least radius of gyration for I sections, L sections and T sections. For this, we need to require the preliminary information regarding the what is the moment of inertia and what is the radius of gyration. In the earlier sessions, we are discussed a lot about these definitions, and for the simple regular rectangular sections like circular sections we did problems on that one. So including that hollow circular section and hollow rectangular section also we have determined the radius of gyration of simple sections. Similarly, symmetrical I section also we are seeing. So their conclusions are like this: the radius of gyration of a rectangle section having the dimension of width b and height h, then this is its radius of gyration, because rxx equal to I by y square root. So that we know that r rxx is equal to square root of I xx ixx by a. So substituted all those values, ixx is equal to bh cube by 12 and area is equal to bh, then substitute you will get this rxx equal to h by 2/3. So similarly ryy is gives us b by 2/3. Similarly for the circular section, so it is rxx equal to ryy because of symmetry on the both sides, and circular is infinitely symmetry. Hence the value of r can generally termed as r is equal to d by 4, or it can be small r by 2, radius by 2. Here d is the diameter and r is the radius. So this is the generally ask. They will post a questions in the ESET asking about the determine the radius of gyration for the circular sections. In order to make it more tough, they will ask hollow sections also in the exam. So frequently they ask about the this hollow circular section. In this particular hollow section of the circular section, we need to, if this is a circle and there is an inner circle, then it is a hollow circular section. So capital D is the outside, capital D is the outside, and whereas the up to this portion, this would be the small d. This inner portion is the small d, right? Using those dimensions, substitute in this equation rxx equal to ryy is equal to square root of, within the brackets, capital D square plus small d square and whole divided by 4. Or we can rewrite the same equation with in terms of the radius also, that is square root of outer circle radius square plus inner circle radius square divided by 2. So this is the how we are going to calculate the radius of gyration for the simple sections where only one or two composite shapes can also be determined with this derivations of rx and ry. And in the particular sums, when they are asking about to find the either rxs or ry, and in some cases they also ask about the find the least radius of gyration. That means we have to calculate the both and we have to report the which is the lower one. So they are asking about the which is the lower one. So the lower quantity among the both values of Rxs and Ryy is known as the least radius of gyration. Is known as the least radius of gyration. So you have to take the lower value to mention as least radius of gyration. So it is meaning that minimum value among the both the values. Least means minimum. So Rxs is and Ryy among these two quantities, which is the minimum. So they are asking in some questions like this. Here you can see that in the rectangular section, its values are different. Rxs will depending upon h value and Ryy is depending upon b value. Now these two values are varying. Now if they are asking about the least radius of variation, you have to find the Rxs and Ryy. Then it should be mentioned as least radius of variation is equal to R minimum is equal to report the minimum value of these two Rxs and Ryy value, whichever is the lower value. Let us say if it is 50 mm, 50.5 mm, let us say, and whereas the Ryy is equal to 23 mm. Then which is the least radius of gyration? So least or minimum, then least, then least radius of gyration is Ryy. Ryy is equal to R minimum, or you can say R minimum is equal to 23 mm. So this is how it is useful to report the minimum values. So in the question, if they are asking about to find the least radius of gyration, you need to find the Rxx and Ryy, then give the value of the minimum value as a least radius of gyration. In the earlier sessions also, we are discussed about the parallel axis theorem. In that equation, we said that if there is a centroidal axis, if there is a centroidal axis is like this, there is a centroidal axis like this. This is the centroidal axis. So I can say this is an XC axis because it is a centroidal axis, XC, let us say. And if I want to know about the moment of inertia about other axis which is parallel to the centroidal axis, for this you need to take the another axis. Let us say here it is an another axis. So this is, so about the central axis it is IXC, about the central axis it is IXC, plus the distance between this one is up to this point it is y bar, up to this point it is y bar, and from this point to this point, from this point to, let us say, from this point to this point is y. This is, therefore y bar up to the centered axis y bar minus references axis. This is the references axis is the y. So you have to subtract. In some cases, this value will give the negative also, but due to the square, it definitely a positive number. Hence, we are not considering this uh, uh, value whether it is negative or positive. We will take the mod of that value because there is a square is already there. Even though it reports the negative, it will automatically converts as a positive. So this is the parallel axis theorem saying that multiply the distance between them. That means this is the distance ultimately y bar minus y will become the d. Hence, this can be termed as d square also, a d square. So this is can be d square. Hence, we are represented here it as a d square, right? So this is how we will get calculate the momentum of inertia which about the an axis which is parallel to the centroidal axis. Right? So it can be represented in such a simple manner. So this d is nothing but the differences between the distances between the both the axes, which is centroidal axis and referenced axis. And we also known about the theorem which talks about the moment of inertia which is perpendicular to the plane. So it is talks about the perpendicular to the plane. Therefore moment of inertia about an axis perpendicular to the plane. In generally it is izz. So that is we are using as izz is equal to the ixx plus iy. So uh, these are the two important theorems we are going to use for the calculation of the momentum of inertia and radius of gyrations as per the question posed. Today in this session we are going to derive the or we are going to solve the some of the moment of inertia and least radius of gyrations mm, problems for the I section, L section and T section with the help of the parallel axis theorem. So with the help of the using parallel axis theorem. So we already understood that what is a parallel axis theorem. So it is nothing but AD square. You need to add with the AD square. It is nothing but AD square. For the centroidal IXX is to be added with this AD square. Then you will get the overall IXX of the particular shape. And similarly for the IYY also we do the same thing for the calculation of the momentum of inertia about any axis which are parallel to the axes. So for I section, let us see how the I section will do for the calculation procedure. Here you can see that if this is an I section, for this if we are going to find out the IXX, you need to locate the total centroid. The first step is you need to find out the total centroid. Find the centroid of the figure that is total find the total centroid of the figure. Then calculate the distances between the centroidal axis of each part to the whole centroid axis. So that is major part in this solution to get the different parts are as a composite shapes, or it can be a built-up sections. So in this case, what we need to do that we should figure out the total centroid of the given shape, and then divide the shape of the figure, and it's notify the x1 x2 x3 like that individual centroids of the parts, and y1 y2 y3 of the individual parts, then obtain the x bar minus x1 x2 x bar minus x2 like that. So that you can obtain the d values. So you need to find out the d values. So this is the d value. So for that you have to calculate the centroids of each figure. Hence, if anybody asking about the moment of inertia for I section or L section or any sections, we have to first know the centroidal position of that particular figure. So with the knowledge of the finding of the centroid in the earlier sessions, we will go through the same thing here also. So find the those values of y1, y2, y3, x1, x2, y3. So the individual centroids of each part. So this is important term, each part. Let us say that for the I section, so here how many parts are there? Here are three parts. So this one is one, and this one is second part, this one is third part. So for each part, their centroids are different. Let us, what is the centroid for the three? This is the centroid part. This is the y1 part. So this distance will be the y1 only for this particular. Whereas for the y2, so from this point to up to this point, it would be the y2. So this is the centroid that you know the calculation. And similarly for the y3, where it will come, this is the centroid point, and from this bottom, and from this bottom, this would be the y3. So from this point to this point, it is the y3. So you need to find out all these individual each part centroids, and you are already known the final centroid. So final centroid is somewhere around here. So final centroid. So for that, so this might be the final centroid from this point to this point. It is y bar. So these are four parts we need to find. So y bar, y1, y2, y3. So because of finding these values, you can obtain the individual d1, d2. So you can find out the distances of the individual points d1, d2, d3. So what would be the d1, let us say? So from this point to this y bar point, this is the d1. When considering to these ones, so this would be the d1. From this point to this point is the d1, because I am considering the distances between the y1 and y bar. Y1 and y bar is the d1. So for this point, let us say for the from this point to this point, it is the d2. This difference is d2, right? From this point to this point, this is the d3. This is the d3. So this is how we need to calculate the each values of the those parallel axis distances, and that get multiplied with the areas, you will obtain the final momentum of inertia of a total figure by summation of all those things. So similar procedure you need to adapt for the y bar also. So for I section, this is the simple procedure you need to follow. If it is a symmetrical section about the y axis also, so then the same procedure will be followed for that also. So what happened if it is the same? So we will go through the problem, then we will understood for that. However, a little explanation is required for that also. So let us say a simple uniform I section. So if this is the uniform I section and its y axis is surprisingly passed through the at the same point throughout the sections. So for this part of 1, this is the part 1, this is the part 2, and this is the part 3. So you can imagine if this is the your 0 point or origin point where the entire section is lies in the first quadrant, then from this point, if this is the distance of the x bar, this is the distance of x bar. Being the symmetry about the y axis, the x3, the distance between from this point is also same as x bar. Even the distance from this point to this point x2 is also the same, and even for the x1 also the distance from this point to this point will be the same for the x1 also. Hence for this particular case of the symmetrical I section about the y axis, due to the it is symmetry about the y axis, hence same vertical line about the y axis, the x1 x2 x3 are equal. Therefore, we doesn't require to calculate the d distances. Here it will be vanishes. This term will be vanishes. This will become in this case is 0. In this case will be the 0 because x bar is equal to x1. So in this particular case what we have to write, x bar minus x. So being x bar and x1 is same. So it will leads to the 0 value, right? So similarly x bar minus x2 is also the same, hence 0. X bar minus x3 is also 0. So hence these particular symmetric about the same y axis and the distances are the same, hence it will leads to the this parallel axis will be vanishes. So normal Iyy values are sufficient to find out the Iyy value. So I can say this is Iyc1, Iyc2, Iyc3. So this is the simple calculations for the I section for the Ixx and Iyy. So note down this difference. Here no, here no AD square term is there, right? But in this case we have the summation of the AD square, right? Whereas for the L section and similar other asymmetrical sections, the procedure for the Ixx and Iyy will be the same. We need to find out the d distances and in the x directions and y directions for the both. You see here also the same condition will be holds. So in this particular, here it is not x bar is not equal to x1 and x bar is also not equal to x2 like that. So let us say a simple um, L section if I taken. This is an L section, let us say. Here it is in generally L section has the two parts. So this one and this two. So if I draw an x bar will come, x bar distance, or if I draw an centroidal x-axis, so this is the centroidal x-axis, right? So this distance from this point is obviously not equal to the, so obviously from this point it's a center is a different value, you are obtaining some another value. And in the same case for this also, for this second part also we have the another value. So we have the another value. So there is a differences of the centroids will be obviously happen. So somewhere here let us say not that much. So this one. So these are the differences we are having. So this total uh, y bar, this is the total y bar, is not equal to y1, right? This is the y1 distances, and for the y2, this is the y2 from this point to this point, it is y2. Therefore, y bar is not equal to y1, y2 and y3. Hence, you require to find out their differences. Hence, this one is the d1 and this one is the d2. The distances are d2. So, these distances have to be found out, and accordingly, their individual centroidal moments are to be summarized to get the I-axis. And similarly, if you take the case of the same L section for the calculation of, let us say this is the L section. So in this case, what happened that, so being this is the L section, now this is X bar is required in this case. So this is the X bar. So X bar is somewhere here. Let us think. This is at somewhere here. So from this point to this point, if it is the X bar, and individual X bars, let us say this is the one, this is the one portion, and this is the second portion. So for this case, this is the one will be from the centroid point, it will be the here, not at this point. It is not the symmetry about the y-axis as in the case of the I section. So now this is not symmetry about the y axis also. So it is not a symmetry. It is not a symmetry, hence not equal. It is not the same vertical line. So it is not the same vertical line. Hence it is, they are not equal to the centroid. So for this case, what we need to do that, just to take the distances of x1. This one is the distance of x1, right? And from this point to up to this point, it is the x2. Now this distance will be the d2. This distance will be the d2, and this distance from this point to this point will be the d1. So this d1 and d2 are nothing but these values, right? So substitute all these values in this one to get the Iy value. So for the L sections and other sections, we need to follow the similar procedure for the both the I-axis and Iyy, because they are not symmetric about the any axes. So with this introduction, let us understood the procedure of the an unsymmetrical figure to determine the moment of inertia. So step by step. So first one, we need to draw the sketch of the figure with the given dimension and inspect for the symmetry axis if any. Place this entire object in the first quadrant such that the extreme left and bottom lines of extents meet at origin O. Find the centroid of the total figure. So this is the up to step 3. It is the similar procedure for the centroid. Now the from 4th to 6th is important for the find out the moment of inertia. Then note down the individual centroids of the parts of the figure like x1, x2, x3, y1, y2, y3. Identify the need of parallel axis theorem at every part of the figure by comparing the part centroid with respect to total figure centroid. So we are taking a differences between the total centroid to the individual part centroid. That means for the y bar minus y1 is gives the d1, y bar minus y2 gives the d2, y bar minus y3 gives the d3, like that. Any number of parts are there, n number of parts we have to find out the dn squares. So keep them aside for the calculation of the moment of inertia using the parallax theorem. and get summarize all the individual values. So using that procedure, let's find the least radius of gyration for asymmetrical eye section with the following dimensions. Top flange plate is 200 by 20 and bottom flange plate is 300 by 30 and web plate is 20 by 500. 20 by 500. So for this particular case, what we need to do that, being it is a asymmetric section, and he is mentioned that there is a top flange. Top flange is 200 by 20. That means this is the this distance is 200. So what you want to say that up to this distance, it is the 200. Yeah? And from this thickness, so we need to draw the figure as the given with the dimensions. That's why we are doing the same thing here. And the bottom flange plate is 300 by 30. The same do the thing. So we draw like this. This is the 300. So this one is the 300. Whereas this thickness is 30. This is the 30. Now you can see that the thicknesses are vary, hence it is not symmetric. If the both are the same, then we can say that some possibility of the symmetry. That's the first point. And width also you can see that this is the 200, this is the 300. Hence this is a not a symmetry section. Hence it is asymmetric section. And web plate is 20 by 500. So thickness is here, it is 20. The thickness is 20. This is the thickness 20, and this entire height from this point to up to this point, it is 500. Right? So this is the total dimension they are mentioned for us to calculate the radius of gyration. And he also mentioned that it should be the least radius of gyration. So we need to find out the rxx, ryy, and then report the lowest value as the least radius of gyration. For this, the same procedure, place the entire eye section into the first coordinate, then determine the values, determine its centroid positions, x bar and y bar. So after finding this x bar and y bar, it is LD by 2, therefore it is the 300 by 2, 150 mm. So follow the same procedure what you learn in the centroid determination. So bottom flange is 300 by 30 because bottom is highest. So bottom 30 by 300 by 30, and top is 200 by 20, and web is 20 by 500. Values are taken from the distances of individual y bar distances like this. This is the 30 by 2. This is height is 30, hence 30 by 2. And up to this point for the second, up to this, from this point we need to add this 30 plus 500 by 2. The total is 500, therefore 30 plus 500 by 2. And for the top flange, 30 plus 500 plus half of this one, therefore 20 by 2, 540. Then multiply area into y to get the y bar value. So in this particular centroid problem, we understood already how to do this centroidal for the x direction and y direction. So represent the same thing in the values here. Right? So not now let us say don't bother about the whether the top range is shown as bigger or bottom flange are shown as bigger. Just to follow the dimensions. So put all the dimensions in the proper way, whether it is a top flange or bottom flange, put the values, right? You will get the correct dimensions of the value of moment of inertia. So for this y bar and y1 and everything you should understood. One second. So in this problem we are finding out the centroidal issues and then figure out at the value of the centroid 221.52 in the y bar direction, and for the x bar it is 150 mm. After finding the centroid and located the centroid value, then we will follow the procedure of finding the parallel axis theorem procedure, because the y1, y2, y3 and y bar are not equal. You can see that from the table also of the centroid. Here you can notice that y1 is 15, y2 is 280, y3 is 540. All are not equal. Even yours y bar, whatever after calculation, it is 221.52. So because the four values are different, we need to apply the parallel axis theorem. So being all the values are different, apply the parallel axis theorem. Therefore, you required the d1 values. So d1 values will be coming by using the y bar value. This is the y bar value. Y bar minus y1, got the 206.52. Similarly, y bar minus y2, y bar minus y3. So in the similar fashion, you will get the all the values of the d1, d2, d3 values by applying the parallel axis theorem. So use this y bar minus individual values are like they are taken from the these centroidal individual axes. They are the individual axes, right? So this is the 221 is the total y bar. So we need to get these d1s, d2, d3 by subtracting y bar minus y1 equal to d1, y bar minus y2, y2, you get the d2, d2 and y bar minus y3, y3, where it is from the third point. So y3, so this distance up to this distance, so you will get the y3 as d3. So these values, so you need to calculate all these d1, d2, d3 values to get the momentum of inertia about the total figure centroids. For that, a simple tabulation procedure is enough for the calculation. So you need to simplify this equation like this by substituting y bar minus y as a d. So I taken all the d values in the from the figure. I noted here for my convenience, and it is also best practice to simplify like this without any mistake. You can do that. So in this particular equation, we have the IXC, that means centroidal IXX of each part. For each part, being a rectangle of the each part of the I section is a rectangle. So IXC is obviously equal to BH cube by 12. So this is equal for all the sections because all are BH cubes, all are the rectangles. So you know that this is a rectangle as the top flange, and this is also a web is also a rectangle, and for the bottom is also a rectangle. Because all three are rectangles, the IXX formula for the IXC formula for the each part is bhq by 12 only. So substitute the values of b and h values from the figure and you get the ixc values. Then you required AD square term for this. Get the areas from the individual parts and write down here those areas. Then you are already calculated the d values. For the first one, d1 has to be squared. So d1 is 206.52. You need to square of that. After getting those squares, just ixc plus ad square is the simple formula we need to use for that addition. Therefore 1 plus 2 into 3, you will use the ixc plus ad square. So you just use these three values, this first value and this is the second value and third value. Therefore you can say that 1 plus 2 into 3, then get this value. Then summarize this one. This is the summation symbol. Because of this one, 1 2 3, these three are to be added. You got this one because it is the sigma, that means summarize it. So this is your final answer of the ixx. So it is very simple calculation procedure. If you understand the distances of the centroidal axis from the original or whole figure centroid, how the each part is varying, if you note down those values, its calculation is very simple. Basic figure values, easy calculation. Now for the IYY, let us try to identify whether it is there any symmetry and all the values are equal or not. So whenever you are trying to do that, so it is understood that it is the same lying on the same axis. So your x bar value is same and x1 value is also be the same, x2 x3 and everything are the same. So all the values from the references point of the 0 axis are the same values. Hence your d will become 0 for all the equations. Therefore d1 and d2, because x bar is equal to x1 and x3 is also equal to x bar. Hence your AD square term will be vanishes. So what will left? Only your centroidal moment of inertia is left. So just to summarize, being it is having the sigma, we need to add the all the three values, all the three values as a equal. Then bh cube for the I-axis, for the IYY you have b cube h. Substitute all those values and as a common nice denominator is 12, then get the value of IYY value. So this is the difference between the asymmetrical axis is available and if there is no symmetrical axis is not available. So if the symmetry is available, your calculation procedure is very simple. D term will be vanishes. If there is no symmetry, you need to calculate the D term. Then in the problem they are asked about the least radius of gyration. They are asked about the least radius of gyration. Therefore you need to find out the Rxx and Ryy. Therefore Rxx is equal to square root of Ixx by a. You know the Ixx value because in this value we have the Ixx term and the total area is this one by adding of all these 1 2 3. So this is the total area. So this is the area, total area, and this is the Ixx value from the table. So just simply for the Rxx, what you need to do that So just have the square root of this term divided by this term. So I am just simply write down these all things like this, like this. So divided by 2 3 0 0 0 0. So you will get the rxx value. So this is the how I get the rxs value. Similarly, the ryy is also the same. Use the instead of ixx, use the iy value for to determine the ryy value. Then they are asked about the least radius. The lesser one of the these among the both you need to report. So this is the lesser one is 59.40. So 59.40 is the least radius of gyration. So let us take the another problem which is using the L section. So in this particular L section we have the two legs. One is a vertical leg and another one is horizontal leg. Generally L section or angle section is given dimensions like this 150 by 100 and its thickness is mentioned like this. Thickness is mentioned. So remember that whenever they are given the first dimension will be the vertical, the first dimension will be the vertical and the second dimension will be the horizontal. So this is the horizontal. So you need to um, make it two parts. For that you can make a part like this. You can make this one as a single part and from this one you can make another part. So this can be possible. So this is the one of the part and this is the second part. The first part is starting from this point. You please differentiate that one. Therefore a will not be equal to now this dimension of this part is should be changed now. Therefore it is nothing but 150 minus 12 is equal to 138 is equal to 138. So this height is 138. So this is one type of division. Right? No, if I want to make it as a total vertical as vertical, that can also be you can do. If I want to make this is a complete vertical, you can make this is a complete vertical. And this will become a second part. Now this will become first and this will become second. Now its dimension will coming from this point to this point. So it will not be the 100 now. Therefore 100 minus 12 the thickness. So here it is the thickness is the 12, right? So that has to be minus. So this is the thickness 12. Therefore that thickness whenever I mention this will become 88. So this is how the dimensions of the vertical and horizontal legs will be vary according to your how extent you are taking the leg dimensions, how you are going to be make a parts of it. So while calculating these centroid and moment of inertia, you need to more precise how you are divided the L section. Right? In this case, I am taking the as a entire horizontal leg as one. So this I take an entire horizontal leg. You can see that I made it a minus 12 for the vertical dimension. That means I taken the part of the first part up to this section only. Up to this is my vertical part. This is only up to this. This is my vertical part. That's why it has taken 138. Right? As the instead of 150, I took 138. Right? So what is my second part? My second part will from the this point to up to from this point to this point. So it is starting from this point. You please understood that up to this point. Hence I took B as 100. So after understood the division of the parts, let carry the procedure of the centroid finding. substitute all the values to get the value of the centroid as we discussed in the earlier. Then I got the final answers of centroid as 24.49. In the x direction it is 24.49. Here it is 24.49, whereas in this direction, y direction, I have 49.49 like this up to this one. So after understanding this centroidal dimensions, let's use these dimensions for the calculation of ixx and iyy with the help of the parallaxis theorem. Let understood from here this point, is it required to find the d1, d2 like that? Yes, you can also identify the possibility of finding also. Here you can see that x bar value is 24.49, but x1 is 6. So x bar is not equal to x1, is not equal to x1. And similarly, if you see that x2 is 50, that means it is also not equal to x2, and so it is required to find the parallaxes distances. Therefore, we definitely find the d1, d2, d3, or d1, d2. Only two parts are there, hence d1 and d2. And for the second part, if you see that even for the y also, for the y bar, we have the 49.49. So let us see what is the value of the y bar. It is y1 is 81. So therefore, y bar is also not equal to y bar is also not equal to y1. See that y bar is 49.49, but y2 is only 6. So hence it is also not equal to y2. Hence it is must to get the using the parallaxis theorem for the both the directions. Hence I applied the same thing here to get the d1 and d2 values. So clearly to understand this one, I mentioned the y1, y2 values and y bar values and their differences here. In this figure it is already mentioned to minus and get the values are like that. So I used the same values to get the d1 and d2 values in the for the ixx and iyy. So this is also for the iyy case also. We solve the values for the d1 and d2 also. Then substitute those values to obtain the ixx for the parallaxis problem theorem as per. So using the same table, substitute being the L section contains also rectangle forms of shapes, hence bh cube by 12 is the for the I axis for the both the equation. Then substitute for the both the parts and get the summarize of the total I xx values. Similarly for the iyy, so this one is also for the iyy, you will get the same value, same procedure, being it is asymmetric about the iyy also, hence get the total values. Same procedure, just substitute those values and you will get the iyy also. Here it is iyy. Okay. Then substitute those values to get the radius of gyration, and here it is our axis is given the minimum value. Being I section, it can be rotated of any shape. Let us say if I say that if I can make this L shape, it is also possible to rotate the same section as in the same. So rxx ryy are interchangeable in this case. Hence rxx ry are interchangeable. Just we need to know the what would be the axis, how we are locating this figure. So that its distance about that axis is known to us. Then accordingly we can resist the torque for the L sections while loading. So with this knowledge, let's try to find the at your uh, convenient time, find the least radius of gyration of the T section as the given dimensions. So it is a simple request to solve the problem at your home. So So do the same procedure. First we find the centroid and then identify the, is there any possibility of the equality of y1, y2, y3, like that, y1 and y2 with the y bar, or is there any possibility of equality of x bar equal to x1 and x2. Then if it is possible, accordingly the simplification can be done and find the least radius of gyration after finding the ixx and iyy. So in this session we are determined the understood how to determine the moment of inertia and least radius of gyration for I section and L section, and the similar procedure is applicable for the T section also. So get solved for the same thing for the T section. Thank you.